Alright, now we want to talk about how will a charge behave if you place it initially at rest in a uniform electric field. So there's a second type of motion here. So we put it in a uniform electric field and it's stationary. Now, wouldn't it experience an electric force? Because a charge will experience a force in an electric field, right now. And therefore, since there's a force, it will cause it to accelerate. That means from rest, it will start to move. Do you understand that? And it will accelerate in the direction of the electric force, and its speed will increase. Do you understand the logic behind it? For example, if you look at this diagram, if I were to connect A to the positive plate, with positive terminal, and C to the negative terminal, so that means this plate is positive, this plate is negative. So if I place an electron which is negatively charged at C, it will experience a force to the right or left? Right. So you see, initially it is stationary, initial speed is 0, but because it experiences a force to the right, it will for sure accelerate to the right. So what will happen is its speed will increase, so you can actually calculate the gain in kinetic energy, which is also the loss in potential energy. And the potential energy we're talking about is not gravitational potential energy, it's electric potential energy. It will gain KE, but according to conservation energy, it will lose electric potential energy. So when it gains KE, its speed will increase, so you can calculate either the KE, the gain in KE, the loss in PE, or you can even calculate the speed it achieves when it reaches A. Okay, all this you can find. So how do we do it? Very simple. The formula is W equals to QV at first. This is the basic formula. How we got this formula is actually a similar formula in the topic of current of electricity, which is PD is equals to W divided by Q. Remember this formula? For those of you who learned it in your Form 5 or earlier, you learned that PD is W divided by Q. Alright? So from this formula, you will be able to get W equals to QV. But don't worry, we will come to this formula again in the next chapter. But for the meantime, you need to remember this equation. So what does W represent? It actually represents the gain in kinetic energy or the loss in potential energy. Alright? And this V represents the PD. Okay? The PD between these two plates. Alright? That's what the V represents. Now, you can also have opposite, in the sense that if let's say you can accelerate an electron, give it a certain speed first, and then direct it to, let's say, a negative plate. So an electron which is negative, it is coming at a very high speed. If it approaches a negative plate, it will slow down or go faster. It will slow down right now due to repulsion. So then it will be lost in kinetic energy, and it will be gaining potential energy. Can also happen. Understand? But this formula, as long as a charge travels across a PD, you can use this formula to find the change in energy. Okay, now, but specifically for this case, because it's moving towards a positive plate, it will be gain in kinetic energy. But if let's say you gave an electron a high speed and it's moving towards the negative plate, it will actually slow down. Then it will be lost in kinetic energy. Do you understand that? But for this case, it's gain in KE. So let's say I wanted to find the speed here when it reaches this plate. Very easy. I break down this W to the change in KE, which is the gain in KE. So what is the gain in KE equals to? The final KE, which is half mv squared, minus the initial KE, which is 0. Because remember, it started from rest. Do you understand that? So equals to QV. So these two formulas are very useful. This first one is to find the change in energy. The second one is to find the speed when it reaches the other plate. So when can we use this? When we can use this formula, these two formulas, whenever you have a charge initially at rest in an electric field and it starts to accelerate, then you can use this. Or there's a charge that you move it against the electric field also can use it. Understand or not? So in summary, we call it motion parallel to the field. Because if your electric field is, for example, horizontally to the left and your electron is moving to the right, isn't it still moving parallel to the field? Or in the sense that if your electron moves to the left, it is still parallel to the field. So whenever a charge moves parallel to the field, we can use these two formulas. Understand?
That's all for today's video. If you're interested in more genuine sharing by other geniuses, please subscribe to our channel and don't forget to turn on the notification bell, ding dong. Also, if you're struggling with one or two past year questions and the mark scheme just doesn't seem to help, Genie has got you covered. Feel free to let us know what question it is by filling in the Google form linked in the description below. GenieUs Hub will get genius teachers to fulfill your request for the solution. Genie will see you next time. Bye-bye.